Of all the star systems discovered in the past 3 decades, one keeps showing up at the top of every scientist's list when the conversation turns to life beyond Earth. It is not because of any single dramatic finding. It is because of the sheer accumulation of details that keep pointing, again and again, in the same direction. 7 rocky planets, all of them roughly the size of Earth, most of them sitting within the zone where liquid water could theoretically pool on a surface, and all of them orbiting a single dim star just 40 light-years away. That star is called TRAPPIST-1, and the James Webb Space Telescope has now pointed its instruments directly at it. The results are more complicated, more surprising, and more scientifically rich than almost anyone predicted. To understand what Webb found, you first have to understand what kind of star these planets are orbiting, because the star does not just set the scene. It actively shapes everything about whether life could exist there at all. TRAPPIST-1 is classified as an ultra-cool red dwarf. It is only slightly larger than the planet Jupiter, but far more massive and dense. Its surface temperature sits at roughly 2,300 degrees Celsius, compared to the 5,500 degrees Celsius surface of our own Sunday. That temperature difference changes everything. Red dwarfs burn so slowly and so efficiently that they are almost immortal on any timescale a human mind can comfortably hold. Stellar models suggest TRAPPIST-1 has another 10 trillion years of fuel remaining. That is 700 times the current age of the universe. Our Sun, by comparison, has roughly 5 billion years left before it begins its slow collapse into a red giant. That longevity sounds like an advantage, and in some ways it is, but it also comes with a serious cost that astronomers have been grappling with for years. Red dwarfs are the most common type of star in the Milky Way. More than 70% of all stars in the galaxy belong to this category. Even Proxima Centauri, our nearest stellar neighbor, is a red dwarf. 50 of the 60 closest star systems to our own contain red dwarfs. So if life can only arise around sun-like stars, then the vast majority of the galaxy is immediately ruled out. That would make the universe a much lonelier place than most people imagine. But the question of whether red dwarfs can host life is genuinely unsettled. There are serious arguments on both sides, and TRAPPIST-1 has become the definitive test case. The central problem with red dwarfs begins with their youth. Because they live so long, their early chaotic phase before they settle into stable middle age is proportionally extended. During those formative billions of years, red dwarfs produce powerful stellar flares at high frequency. These flares flood nearby space with ultraviolet radiation and high-energy particles, and anything orbiting close enough to be in the habitable zone is right in the line of fire. TRAPPIST-1, to its credit, is one of the calmer red dwarfs astronomers have found. It flares approximately 30 times less often than a typical star of its class. But even a calm red dwarf by these standards would be considered extraordinarily violent compared to our Sunday. The worst geomagnetic storm ever recorded at Earth was the Carrington event of 1859, a once-in-a-century occurrence. TRAPPIST-1 is estimated to produce a flare of that magnitude more than once every 2 days. Now picture standing on the surface of one of its planets. The star above you would appear more than 4 times the angular size of our Sun, glowing in deep red-orange tones, painting the sky in a perpetual sunset. And then, without warning, a ribbon of plasma arcs across the face of that star, releasing more energy in minutes than some stars emit in hours. That radiation hits the atmosphere. Over millions of years, it strips gases away, and for a planet without a strong magnetic field, there may be nothing left. This is the core tension at the heart of the TRAPPIST-1 system. The very conditions that make it interesting, proximity to the star, long stellar lifespan, potentially stable climate, are the same conditions that make it hostile. Understanding which force wins requires data, and data is exactly what the James Webb Space Telescope was built to provide. The TRAPPIST-1 system was first identified in 1999 when the star itself was catalogued. But the planets were not discovered until 2017, when the TRAPPIST Optical Robotic Telescope Network, operating from 2 sites, one in the mountains of Chile and another in the Atlas Mountains of Morocco, detected the full planetary lineup using a technique called transit photometry. Transit photometry works by continuously monitoring the brightness of a star. When a planet passes between the star and the observer, it blocks a small fraction of the light, producing a measurable dip in apparent brightness. By timing these dips precisely and tracking them over many orbital periods, astronomers can determine the size of the planet, its orbital period, and its distance from the star. Using this method, the TRAPPIST telescopes and later the Spitzer Infrared Space Telescope confirmed the existence of 7 rocky planets, all of them at least approximately Earth-sized, all of them within a remarkably compact orbital architecture. The outermost planet still sits closer to TRAPPIST-1 than Mercury does to our Sunday. Mercury orbits our star at roughly 58 million kilometers. The outermost TRAPPIST-1 planet orbits at only 9 million kilometers. All 7 worlds are crammed into a space smaller than the innermost orbit of our solar system. That compactness is not just an interesting geometric fact, it has direct implications for the planets themselves. Because they orbit so close to a relatively dim star, 6 of the 7 sit within what astronomers call the habitable zone, the range of distances where liquid water could theoretically exist on a surface. In our solar system, that zone spans from roughly the orbit of Venus to slightly beyond the orbit of Mars. Around TRAPPIST-1, it is squeezed inward dramatically, but the planets happen to be squeezed inward just as much, placing multiple worlds in exactly the right spot. What the James Webb Space Telescope brought to this picture was something the TRAPPIST telescope network could never achieve on its own. Webb is sensitive enough and its instruments precise enough to analyze the chemical composition of planetary atmospheres from 40 light-years away. It does this through a technique called transmission spectroscopy. When a planet transits its star, the starlight that filters through the thin shell of the planet's atmosphere is subtly altered. Different molecules absorb light at different specific wavelengths. Carbon dioxide absorbs at particular infrared wavelengths. Methane absorbs at others. Water vapor has its own spectral fingerprint. By comparing the spectrum of the star during a transit with the spectrum recorded outside of transit, astronomers can identify which molecules are present in the planetary atmosphere. Webb's near-infrared spectrometer, known as NIRSpec, is specifically designed to detect these signals, and TRAPPIST-1 turns out to be an ideal target for this kind of measurement for a reason that might seem counterintuitive at first. The star is dim. Because the star is so faint, even a small planet passing in front of it produces a comparatively large drop in brightness. A larger signal is easier to measure. As a result, the data Webb has collected on TRAPPIST-1 is roughly 10 times more sensitive than any equivalent dataset for any other planetary system. Scientists are working with a level of atmospheric detail they simply cannot access anywhere else at this scale. The team that secured guaranteed observation time on Webb immediately focused their attention on TRAPPIST-1. They call themselves the Deep Reconnaissance of Exoplanet Atmospheres through Multi-Instrument Spectroscopy Team. And what they found when they turned Webb's instruments on each planet, in turn reshaped the picture of this system in important ways. The innermost planet, TRAPPIST-1b, orbits at only 1.7 million kilometers from the star. A year there lasts just 36 hours. Its size is slightly larger than Earth, but its mass is similar, giving it a surface gravity of about 80% of Earth's. Before Webb, models suggested this planet might have a thick, dense atmosphere rich in carbon dioxide, something like a supervenous baking under intense radiation. Webb's measurements told a different story. The dayside surface temperature of TRAPPIST-1b came in significantly cooler than a thick atmosphere would produce. It sits at roughly 227 degrees Celsius, hot but not nearly hot enough to indicate the kind of greenhouse warming a substantial atmosphere would create. The conclusion was straightforward. TRAPPIST-1b has little to no atmosphere. It is a bare, scorched rock with no chance of hosting life as we understand it. TRAPPIST-1c, the second planet, orbits at 2.4 million kilometers and completes a year in 58 hours. It is about 10% larger and more massive than Earth, giving it gravity comparable to Earth's. Early models again predicted a thick water vapor or carbon dioxide atmosphere. Webb again disagreed. The measured surface temperature was cooler than expected, making it the coolest rocky exoplanet ever, categorized by thermal emission measurement. This ruled out a substantial atmosphere and strongly suggested the planet formed with very little water content. If there were a meaningful atmosphere, some water vapor would have been detectable. There is none. TRAPPIST-1c almost certainly has either no atmosphere or one thinner than the already sparse atmosphere of Mars. TRAPPIST-1d sits at 3.4 million kilometers from the star and takes 97 hours to complete one orbit. It is smaller than Earth, about 70% of Earth's diameter and only 30% of Earth's mass, placing its surface gravity at just under half of what we experience here. That puts it on the inner edge of the habitable zone, where temperatures are warm but potentially manageable. It receives about 4.3% more starlight than Earth does. Webb's readings here are more ambiguous. No water, methane, or carbon dioxide has been clearly detected in the atmosphere. But that absence does not necessarily mean no atmosphere exists. There are hints in the data that TRAPPIST-1d might have a volatile layer, possibly a thick obscuring atmosphere or a subsurface ocean that could be interfering with the signal. Some theoretical models actually suggest this planet could be an ocean world with more than 250 times the volume of water in Earth's oceans combined. Other models suggest something more like Venus, and still others suggest no atmosphere at all. Webb has not yet been able to rule any of these scenarios definitively in or out. The tidally locked nature of these planets makes the atmospheric question particularly consequential. All 7 worlds almost certainly keep one face permanently toward the star and one face permanently in darkness, a consequence of their extreme orbital proximity. A planet with no atmosphere in this configuration is a world of extremes. The day side is scorched by constant radiation. The night side is a frozen wasteland, cold enough to freeze even gases out of any remaining thin atmosphere. There would be no weather to speak of, no circulation to moderate temperatures, and almost certainly no liquid water in any stable form. But a planet with a thick enough atmosphere changes completely. Venus, despite its hellish surface conditions, has an atmosphere so thick that its surface temperature varies by only a few degrees between its day and night sides. A comparable atmosphere on a tidally locked world could distribute heat from the permanent day side to the permanent night side, preventing atmospheric collapse and potentially allowing liquid water to exist across much of the surface. An intermediate case is also possible. A planet with a modest atmosphere and a partial ocean might only be habitable along a band of territory in permanent twilight, the boundary region between eternal day and eternal night. This is sometimes called terminator habitability, and while it sounds restrictive, a twilight band on a rocky world could still represent an enormous amount of surface area. TRAPPIST-1f sits at 5.8 million kilometers from the star, completing a year in roughly 220 hours or about 9 Earth days. Its size is close to Earth's, but its density is lower, indicating a different composition. Recent studies suggest it is likely 20% water by mass. At the distance it orbits, that much water in the context of its temperature profile would likely exist as a massive greenhouse gas layer, turning the planet into what astronomers call a steam world. The surface pressure and temperature under such conditions would likely be extreme, comparable to the deep layers of gas giants in our own solar system, rather than anything hospitable to life as we know it. TRAPPIST-1g is slightly larger than Earth and orbits at 7 million kilometers, completing a circuit every 12 Earth days. Water has again been detected in association with this planet, and it sits at the outer edge of the habitable zone, making it a candidate for further study, though detailed atmospheric characterization has not yet resolved its composition clearly. TRAPPIST-1h is the outermost of the 7 known planets, orbiting at 9.3 million kilometers with a year lasting 19 Earth days. It is the smallest and least dense of the set, with surface gravity comparable to Earth's moon. At this distance from a red dwarf, temperatures would be low enough that any surface water would be ice. Some theoretical models suggest a hydrogen-rich atmosphere could act as a sufficient greenhouse to maintain liquid water, but observational data remains sparse, and this planet is generally considered the least likely habitat for life under current models. And then there is TRAPPIST-1e. TRAPPIST-1e sits at approximately 4.2 million kilometers from the star and completes an orbit every 92 hours, or just under 4 Earth days. Its size is roughly 90% of Earth's diameter, placing it within the range where we might expect similar geological processes, similar volcanic activity, and a similar potential for generating and maintaining a secondary atmosphere. Most critically, it sits almost precisely in the middle of TRAPPIST-1's habitable zone, receiving about 2/3 of the stellar energy Earth gets from our Sunday. When the DREAMS team analyzed Webb's early observations of TRAPPIST-1e, something unusual happened. The data did not quickly rule out an atmosphere, as it had for planets B and C. Instead, the readings were intriguing in ways that kept scientists examining them carefully. What they established first was what TRAPPIST-1e does not have. It does not have a primordial atmosphere, the original hydrogen and helium envelope a planet acquires during formation. That kind of atmosphere would have been stripped away by the star's early radiation bombardment. It also does not appear to have a thick carbon dioxide atmosphere like Venus, nor a thin, sparse one like Mars. Those scenarios have been made significantly less likely by the available data. This matters because it narrows the field. The remaining possibilities are either no atmosphere at all, which cannot yet be ruled out, or something more interesting. And the most interesting possibility is an atmosphere compositionally similar to Earth's, dominated by nitrogen with contributions from water vapor, carbon dioxide, or methane, and maintaining a surface pressure of around 1 bar. That is the pressure at Earth's sea level. An atmosphere like that, on a tidally locked planet orbiting in the middle of the habitable zone, could be enough to circulate heat from the permanent day side to the night side and maintain a global surface ocean. If that were confirmed, it would be among the most significant scientific findings in human history. The current data, however, slightly favors a different scenario. TRAPPIST-1e may be a cold planet without a global ocean, its atmosphere dominated by methane in a configuration that creates a reverse greenhouse effect rather than warming the surface. Here is why that matters mechanically. Our sun outputs most of its energy in visible light. Methane in an atmosphere absorbs some infrared radiation but does not strongly block visible light, so on Earth, methane is a warming gas. TRAPPIST-1, being so much cooler, outputs a larger fraction of its energy in the near-infrared range. Methane can absorb that near-infrared energy before it even reaches the surface, re-emitting it back into space. The result is a planet that is actually cooled by its own atmosphere rather than warmed by it. For a tidally locked world in this configuration, liquid water might exist only on the permanently illuminated face of the planet, in localized warm regions where the geometry of starlight and atmospheric circulation allows temperatures above freezing. This is more limited than a global ocean, but it is not biologically inert. Charles Darwin's warm little pond hypothesis, one of the oldest serious frameworks for the origin of life, requires only a small body of liquid water with an energy source and access to organic chemistry. Tidally locked planets with localized liquid water regions might satisfy precisely those conditions. There is another reason not to dismiss TRAPPIST-1e despite its challenges. Atmospheric modeling suggests it might have its own magnetic field, generated by the movement of conducting material in its interior, analogous to the process that creates Earth's magnetic field through the convection of molten iron and nickel in our outer core. If TRAPPIST-1e's orbit has even slight eccentricity, the gravitational interaction between it and its orbital neighbors would repeatedly flex and compress the planet's interior, generating internal friction and heat. This process is estimated to produce tidal heating of roughly 0.18 watts per square meter inside the planet. That is approximately 24 times the tidal heating rate of Earth's interior. The most dramatic known example of this process in our solar system is Io, one of Jupiter's 4 large moons. Io is tidally locked with an eccentric orbit, and the gravitational tug-of-war between Jupiter and the other large moons constantly deforms its interior. The result is the most volcanically active body known in the solar system, with hundreds of active volcanoes and continuous resurfacing on geological timescales. TRAPPIST-1e could have an interior energized by a similar mechanism, maintaining volcanic activity that replenishes the atmosphere from below, even as stellar radiation strips it away from above. That balance between replenishment and depletion is at the heart of whether any of these planets could sustain an atmosphere over billions of years. A planet that can replace what it loses has a chance. A planet that cannot is condemned to be stripped bare. The question of timing is also crucial and underappreciated. Red dwarfs live enormously long lives, but their chaotic early phase is proportionally extended. TRAPPIST-1 is expected to live for roughly 10 trillion more years. Its early violent period, before it settled into something approaching stability, may have lasted several billion years. During that time, the TRAPPIST planets were being bombarded by intense radiation and stripped of any early hydrogen-rich envelopes. If a planet's secondary atmosphere, generated from volcanic outgassing rather than primordial gas capture, could not establish itself before roughly 5 billion years, it may never develop a stable one at all. The race between atmospheric generation from volcanic activity and atmospheric destruction from stellar radiation is one that plays out invisibly and over timescales that dwarf human civilization. We are trying to read the final score of a game that started before Earth existed. And here is where the situation becomes genuinely fascinating rather than merely discouraging. The same flares that strip atmospheres away may also be necessary to create the chemical precursors of life. Ultraviolet radiation from stellar flares can drive chemical reactions that produce RNA nucleotides, the molecular building blocks that form the backbone of ribonucleic acid. RNA is central to the metabolism of every living organism ever observed on Earth. The current leading hypothesis for the origin of life on our planet involves RNA, not DNA, as the first self-replicating molecule. If that hypothesis is correct, then ultraviolet radiation is not just a hazard to life, it is a requirement for its origin. This creates a scenario where the very star that threatens to destroy a planetary atmosphere is also the star providing the energy to chemically assemble the first replicating molecules. TRAPPIST-1, in its violent youth, may have been simultaneously sterilizing its planets and priming them for eventual biology. Now, having settled into a calmer main sequence phase, it produces lower ultraviolet and X-ray output than it did billions of years ago. If any of these planets manage to hold onto an atmosphere through that turbulent period, they might now be in one of the most biologically promising environments we have yet found. Water has been detected in association with multiple planets in the system. The star, while not perfectly quiet, is substantially calmer than typical red dwarfs. Several planets have sizes, masses, and orbital positions that fall within reasonable biological parameters, and Webb is now capable of detecting atmospheric signatures with a sensitivity 10 times greater than any previous instrument has managed at this distance. Scientists on the DREAMS team have already used the insights from early Webb observations to refine their measurement techniques, developing more precise methods for disentangling atmospheric signals from the stellar noise that TRAPPIST-1 itself generates. The star emits methane as part of its own photosphere, which can contaminate spectra taken during planetary transits. Distinguishing between methane in the planet's atmosphere and methane in the star's own emission is one of the primary technical challenges they are now working to solve. Webb has now observed 4 separate transits of TRAPPIST-1e. Each transit adds data. Each dataset allows scientists to stack observations, improving the signal-to-noise ratio and bringing faint atmospheric signatures into sharper resolution. The most recent analysis tentatively suggests methane may be present in the planet's atmosphere, but the team is careful not to overinterpret data that could be contaminated by the star itself. What they are working toward is a definitive detection or absence of carbon dioxide, which would be a cleaner indicator of a secondary atmosphere than methane. Carbon dioxide in a rocky planet's atmosphere is a strong signal that the planet has experienced sustained volcanic outgassing, the same process that built Earth's early atmosphere before life began converting it into something breathable. Finding carbon dioxide around TRAPPIST-1e would be the strongest evidence yet that at least one of these worlds developed a real, chemically complex atmosphere. Not finding it would be revealing in a different way. An absence of carbon dioxide might indicate that any atmosphere present is dominated by different chemistry, or that the planet is genuinely airless. Either result is scientifically valuable. The telescope that might finally answer the deepest question is not Webb. It is the proposed Habitable Worlds Observatory, a large space telescope currently in conceptual development with a projected launch in the early 2040s. Where Webb was designed to study the universe across cosmic timescales and distances, the Habitable Worlds Observatory would be specifically engineered to detect the biosignature gases of living planets, oxygen, ozone, methane in disequilibrium, and other molecular combinations that chemistry alone cannot easily explain. A planet with oxygen and methane in its atmosphere simultaneously is deeply anomalous. Chemistry rapidly converts methane in the presence of oxygen into carbon dioxide and water. If both gases are present in detectable quantities, something is continuously replenishing them. On Earth, that something is biology. The Habitable Worlds Observatory would be capable of detecting these disequilibrium signatures around nearby Earth-like planets. TRAPPIST-1e, sitting 40 light-years away, would be exactly the kind of target such an instrument was designed for. Until that instrument exists, the conversation continues through the data Webb is accumulating, transit by transit, observation by observation. The TRAPPIST-1 system has already taught astronomers things they did not expect. TRAPPIST-1 B and C, predicted to have thick atmospheres, turned out to be bare rocks. The inner system is emptier than models suggested. The middle of the habitable zone, centered on TRAPPIST-1e, has turned out to be more ambiguous and more scientifically rich than anyone anticipated. That ambiguity is not a failure. It is exactly the kind of result that distinguishes a genuinely interesting system from one that confirms only what was already known. The history of the search for life beyond Earth is full of moments where confident expectations were overturned. Mars was expected to be biologically active in the 1970s, and the Viking landers found chemistry but not biology. Titan was expected to be simple, and Cassini found it covered in hydrocarbon lakes and complex organic chemistry. Europa was expected to be inert, and gravity measurements revealed a global liquid water ocean beneath its ice. Enceladus surprised everyone by actively venting water vapor and organic molecules into space. The pattern is not that life is found where expected. The pattern is that habitable conditions, broadly defined, keep showing up in places where they were not expected, and that our definitions of habitability keep expanding as we learn more. TRAPPIST-1e may turn out to be barren. The star may have stripped its atmosphere before life had any chance. The tidal locking may create conditions too extreme for any biology to gain a foothold. These are genuine possibilities that the data so far cannot rule out. But it is also possible that 40 light years from here, on a planet a little smaller than Earth, orbiting a dim red star in permanent sunset, there is an atmosphere, and in that atmosphere, the chemistry of life is happening. Not because the conditions are gentle, but because they have had 10 billion years to work, and because the fundamental processes that produce complex molecules from starlight and minerals and liquid water are not peculiar to Earth. Life, as best we understand it, is chemistry, and chemistry does not care where it happens. The search for that chemistry, at this distance, with this level of precision, is one of the most technically demanding scientific programs ever undertaken. The James Webb Space Telescope represents the current limit of what human engineering has achieved in this direction. It is reading the atmosphere of a planet the size of Earth 40 light years away by measuring how the light of a distant star changes as that planet passes across its face. The signal it is detecting is a fraction of a percent of the total light from that star. That this is even possible is remarkable. That it is producing scientifically meaningful results is extraordinary. What comes next in the TRAPPIST-1 story is more Webb observations, continued refinement of atmospheric models, improved methods for separating planetary signals from stellar contamination, and, eventually, if funding and timelines hold, the Habitable Worlds Observatory. Each step brings resolution to a picture that is currently blurry at the edges. The honest scientific position right now is uncertainty. TRAPPIST-1e might have a habitable atmosphere, it might not. The data is genuinely ambiguous, and that ambiguity is not a limitation of the scientists studying it. It is a reflection of how difficult the measurement is and how carefully researchers are treating results that could easily be overinterpreted. That caution is appropriate. A claim of biosignatures around a nearby world would be the most consequential scientific announcement in human history. The bar for that claim has to be proportionally high. Webb is in the process of building the evidence that will eventually let astronomers say something meaningful, one way or the other. In the meantime, the system remains what it has always been: the best nearby test of whether Earth-like biology can happen around a red dwarf. A system with more potentially habitable worlds than any other we have found. A target close enough to study in detail, but far enough away to keep its secrets a little longer. The universe is not making this easy, but then it never does. The most important answers tend to be the ones that require the most patience, the most precision, and the most willingness to sit with uncertainty until the data is good enough to say something true. If you find this kind of question worth sitting with, the kind that takes years of observation and careful thinking to approach, you are probably the kind of person who would appreciate more content in this direction. Subscribing means you will see new videos as this story develops, because the TRAPPIST-1 story is far from over. Webb will continue observing, new transits will be analyzed, and at some point in the next decade or so, the picture will sharpen considerably. The real question is not whether TRAPPIST-1e is habitable in the abstract. The question is whether the specific sequence of events that produce life on Earth, liquid water, chemical gradients, energy input, molecular self-organization, and enough time can be replicated in a star system with a completely different kind of star, in a completely different orbital architecture, around worlds that never see a sunrise or a sunset because they are locked in permanent orientation toward their sun. If the answer is yes, then the galaxy is almost certainly full of life, because red dwarfs are the dominant stellar type and they exist in numbers that dwarf every other category of star combined. 7 out of every 10 stars you see when you look at the night sky belong to this class, and most of them are too dim to see without a telescope. If life can arise around TRAPPIST-1, then the universe has been running that experiment around billions of red dwarfs for billions of years, in billions of star systems we have not yet begun to characterize. If the answer is no, if red dwarf planets are invariably too radiation blasted or too poorly equipped to hold onto atmospheres, then the conditions for life may be far more restricted than optimistic estimates suggest. The galaxy might be quieter, more empty, with life clustered around the minority of stars that share the Sun's characteristics, rather than spread broadly across every class of star that exists. Either answer would be profoundly important. Either answer would reshape how we think about our place in the universe, about the probability of intelligence arising elsewhere, about whether the cosmos is the kind of place where life is a common outcome of chemistry or a rare accident of circumstance. TRAPPIST-1e cannot answer that question by itself, but it is, right now, the best place in the known universe to begin finding out. To fully appreciate why TRAPPIST-1e is the focus of so much scientific attention, it helps to understand exactly what the habitable zone concept actually means and what it misses. The term was coined decades ago as a simple geometric calculation. Given a star's luminosity and a planet's albedo, at what distance would liquid water remain stable on a rocky surface? The inner edge of the zone is set by the runaway greenhouse threshold, beyond which water vapor creates a self-reinforcing warming loop that boils the oceans. The outer edge is set by the maximum greenhouse effect, beyond which carbon dioxide begins to condense rather than warm. Between those boundaries sits what theorists call the circumstellar habitable zone. But that calculation assumes a specific kind of atmosphere. It assumes a nitrogen-dominated atmosphere with carbon dioxide and water vapor as the primary greenhouse gases. Change the atmospheric composition and the boundaries shift. A planet with a hydrogen-rich atmosphere extends the habitable zone dramatically outward because hydrogen is an extraordinarily efficient greenhouse gas. A planet with an anti-greenhouse gas like methane at TRAPPIST-1 can shift temperatures downward from what the habitable zone calculation predicts. The habitable zone is a useful first approximation, not a definitive boundary. This is why TRAPPIST-1e's atmosphere matters so much more than its orbital position alone. Knowing it sits in the middle of the geometric habitable zone tells you it receives approximately the right amount of energy. Knowing what its atmosphere does with that energy tells you what actually happens on its surface. And the atmosphere question connects directly to something that took decades of scientific debate to resolve, even for planets in our own solar system. Early in the space age, astronomers looking at Venus through ground-based telescopes saw a thick cloud layer and assumed the surface was probably warm and humid, possibly even jungle-like. The temperature at the cloud tops was measured and seemed tolerable. Then the Soviet Venera probes descended through the atmosphere and transmitted data from the surface. The temperature was 460 degrees Celsius. The pressure was 90 times Earth's. The dense carbon dioxide atmosphere had trapped enough heat to melt lead. Venus taught astronomers that surface conditions are not simply a function of distance from the star. They are a function of atmospheric chemistry, and atmospheric chemistry can diverge dramatically from what simple models predict. A planet at the same distance as Earth, receiving the same energy, can be a furnace or a paradise depending entirely on what gases are present in its atmosphere and in what proportions. This lesson applies directly to the TRAPPIST-1 system. TRAPPIST-1b receives significantly more stellar energy than Venus receives from our Sun, yet its measured temperature is lower than expected if it had a thick atmosphere. The dayside measurement is consistent with a dark, airless surface absorbing and re-radiating energy directly, with no atmospheric blanket to trap it. This is a planet that absorbed the lesson of Venus in reverse. Instead of a runaway greenhouse, it appears to have no greenhouse at all. TRAPPIST-1c is similar. It receives about twice the stellar flux Earth receives from our Sun, which puts it inside what most models would call the inner edge of the habitable zone. For it to be cool enough to be in a habitable state would require a highly reflective surface or an extremely thin atmosphere. Webb's measurements confirmed that the surface is cooler than expected for a planet with a substantial atmosphere, pointing again toward a largely airless world. The progression from B to C establishes a pattern that makes D, E, F, G, and H scientifically interesting precisely because they sit further out, where the energy budget is lower and the possibility of retaining volatiles is higher. Planet D is particularly intriguing because its low mass complicates the story. A planet with only 30% of Earth's mass has weaker gravity and a smaller gravitational grip on atmospheric gases. Lighter gases escape more easily. This is part of why Mars, with about 11% of Earth's mass, has lost most of its early atmosphere. The internal heat of a planet also scales with mass. A smaller planet cools faster, reducing the volcanic activity that replenishes the atmosphere from below. TRAPPIST-1 D. At 30% Earth mass, sits in an awkward intermediate range where it might be massive enough to retain some atmosphere, but small enough that the processes that generate and maintain it are weaker than they would be on a full Earth mass world. And yet, Planet D also sits on the inner edge of the habitable zone, meaning it receives enough energy that even a modest greenhouse effect could maintain liquid water. If it does have any atmosphere at all, temperatures might be warmer than the outer planets, potentially providing enough energy for complex chemistry. The ambiguity in Webb's measurements of TRAPPIST-1d is frustrating from a definitive answer perspective, but genuinely interesting from a scientific one because it means the planet occupies a parameter space where multiple outcomes remain physically plausible. The question of water content across the TRAPPIST-1 system is one that planetary formation theorists have been grappling with seriously since the system was confirmed in 2017. Where did these planets form? Did they accrete from material close to the star, which would have been dry, rock, and metal material? Or did they form further out and migrate inward, picking up ice-rich material from beyond what's called the snow line, the distance at which water freezes in a protoplanetary disk? The snow line in the early TRAPPIST-1 system would have been at a very short distance from the star, given how dim the star is. Planets forming just outside that line would have had access to abundant ice, and if they migrated inward to their current positions, they might have arrived with substantial water inventories. Models of TRAPPIST-1's formation suggest that some of the planets, particularly D and E, could have formed in a water-rich region and migrated inward, potentially carrying enough water to form deep global oceans if the temperature profile allowed liquid water to persist. This is consistent with the density measurements of the planets. TRAPPIST-1 D and E are both less dense than pure rock would suggest, implying that they contain some fraction of material lighter than silicate rock, possibly water, possibly carbon compounds, possibly some combination. The exact fractions are not yet determinable from the available data, but the low densities are a strong hint that these are not simply miniature versions of Mercury or the Moon. On Earth, liquid water covers about 71% of the surface to an average depth of about 3.6 kilometers, but the total water inventory of the planet is actually quite small relative to the planet's overall mass, roughly 1 part in 4,000 by mass. If TRAPPIST-1 D or E contains significantly more water, the surface might be covered by an ocean hundreds of kilometers deep, creating what theorists call an ocean world. This is an intriguing but potentially limiting configuration for life, because ocean worlds can develop high-pressure ice phases at depth that prevent water from circulating through the rocky mantle. On Earth, the rock-water interface of the ocean floor is where some of the most important geochemical cycling happens, including the release of minerals and energy sources that sustain the deepest ecosystems we know of. A planet with an ocean so deep that the seafloor is not rock, but high-pressure ice might be chemically isolated in ways that limit the development of complex chemistry. But this is not a certainty. The diversity of life on Earth in environments once thought uninhabitable, from hydrothermal vents in the abyssal ocean to subsurface aquifers kilometers below the surface to highly acidic lakes and alkaline hot springs, suggests that chemistry finds ways forward in surprising places. Whatever theoretical framework is applied to TRAPPIST-1, the empirical lesson of Earth's biosphere is that life is not easily restricted by the boundaries humans initially imagined for it. The question of planetary magnetic fields is one of the most important and most difficult aspects of assessing TRAPPIST-1's planets. Earth's magnetic field is generated by convection in the outer core, a shell of liquid iron and nickel surrounding the solid inner core. As this conducting liquid flows under the influence of the planet's rotation and thermal gradients, it generates electrical currents, and those currents generate a magnetic field. The field extends far beyond the planet's surface, forming the magnetosphere, which deflects the charged particles in the solar wind and prevents them from directly impacting the upper atmosphere. Without this shield, the solar wind would gradually erode the upper atmosphere over geological timescales. Mars is the most dramatic example of this in our own solar system. Mars lost its magnetic field approximately 4 billion years ago when its core cooled and solidified. Once the field was gone, the solar wind had direct access to the upper atmosphere. Atmospheric loss accelerated, and over hundreds of millions of years, Mars went from a planet that geological evidence suggests had liquid water on its surface to the cold, thin atmosphered world it is today. The magnetic field is not merely a protective feature, but a prerequisite for maintaining the kind of dense atmosphere that liquid water requires. The TRAPPIST-1 planets face a much more intense version of the same challenge. TRAPPIST-1 even in its current calmer phase, produces far more high-energy particle radiation than our Sunday. A planet without a magnetic field orbiting TRAPPIST-1 would be exposed to orders of magnitude more erosive radiation than Mars ever experienced from our Sunday. The atmospheric lifetime of an unshielded rocky planet in the TRAPPIST-1 system would be dramatically shorter than on Mars. Whether TRAPPIST-1e has a magnetic field depends on whether its interior is still hot enough to maintain a liquid metallic outer core with active convection. Larger planets cool more slowly because their volume grows as the cube of the radius, while their surface area grows only as the square, meaning the interior heat is more effectively insulated. At approximately 90% of Earth's radius and a similar composition, TRAPPIST-1e might have an interior thermal profile similar enough to Earth's to maintain active core convection and therefore a functioning magnetic field. The tidal heating mechanism discussed earlier adds another pathway to a hot interior. If TRAPPIST-1e's orbit is even slightly eccentric, the continuous flexing and compression of the planet's body by tidal forces would deposit energy directly into the mantle and potentially the core. This could extend the period during which the interior remains hot enough for a dynamo effect. For a planet whose orbital period is measured in hours rather than years, the tidal interactions between planets in such a compact system are not negligible. The resonant gravitational relationships between the TRAPPIST-1 planets, which maintain the stability of the system over long timescales, also continuously perturb each planet's orbit in ways that could sustain tidal heating. The TRAPPIST-1 system, it turns out, is not a collection of isolated planets, but a gravitationally coupled system where each planet's properties are partially determined by the influence of its neighbors. This kind of coupling has no parallel in the inner solar system, where the planets are spread over distances far greater than the entire extent of the TRAPPIST-1 system. Studying one TRAPPIST-1 planet in isolation is incomplete. Understanding the system requires accounting for the web of gravitational interactions between all 7. This is one reason why the Webb observations across multiple planets, rather than focusing exclusively on the most promising candidates, are so valuable. Each planet's atmospheric state, if determinable, provides data about the star's radiation output, the system's dynamical history, and the range of outcomes possible for rocky planets in this environment. Even the barren rocks of TRAPPIST-1 b and c tell the story of what the star's radiation has done to the inner system over billions of years. That context frames the interpretation of everything Webb sees further out. There is another dimension to the TRAPPIST-1 investigation that rarely makes it into popular coverage, but is scientifically essential. These observations are calibration exercises for the entire field of exoplanet atmospheric science. Every technique Webb applies to TRAPPIST-1, every correction factor researchers develop for separating stellar contamination from planetary signal, every model they build to interpret ambiguous data becomes part of the toolkit that astronomers will apply to every other system they observe. The difficulties encountered with TRAPPIST-1 drive instrument improvements, analysis refinements, and theoretical developments that will matter for characterizing exoplanet atmospheres around every other star studied by current and future observatories. In this sense, TRAPPIST-1 is not just a candidate for life, it is a training ground for the science that will eventually find life wherever it turns out to be. The 40 light-years separating us from this system is not a barrier, but a laboratory distance, close enough that the signal-to-noise is meaningful, far enough that the detection challenges push the field toward better methods. The history of observational astronomy is full of moments where a challenging target forced a technical breakthrough that then enabled discoveries far beyond the original goal. The development of interferometry to resolve stellar diameters led to the detection of stellar companions. The creation of coronagraphs to block stellar light while studying stellar coronae led to the first direct imaging of exoplanets. The adaptation of spectroscopic techniques for stellar composition analysis led to the first indirect detection of exoplanet atmospheres. The difficulty of seeing something that should be visible drives the invention of tools that end up seeing things no one initially imagined. TRAPPIST-1 is playing that role right now. The DREAMS team's efforts to pull atmospheric signals out of noisy Webb data are producing analytical frameworks that will make every future observation more productive. The star's methane contamination problem, frustrating as it is, has driven the development of stellar spectral models that more accurately represent cool red dwarf photospheres, which will benefit the characterization of dozens of other red dwarf planetary systems. This cumulative dimension of science, where each investigation builds the infrastructure for the next, is often invisible in the narrative of specific discoveries. But it is arguably the most important thing happening at the frontier of exoplanet research right now. The next decade of Webb observations, combined with ground-based support from large observatories and eventually the extremely large telescope and the 30-meter telescope, both currently under construction, will continue building the atmospheric picture of the TRAPPIST-1 planets. Each new transit adds data. Each additional season of observations reduces statistical uncertainty. The tentative methane hint in TRAPPIST-1E's spectrum may resolve into a clear detection, or it may dissolve into noise as more data is added. Either outcome advances the science. What astronomers are specifically hoping to achieve in the next several years is a detection or definitive non-detection of carbon dioxide in TRAPPIST-1E's atmosphere. Carbon dioxide is Webb's most accessible atmospheric tracer for rocky planets. It has strong absorption features in the mid-infrared that NIRSpec can detect, even at the signal levels achievable for TRAPPIST-1. If carbon dioxide is present at Earth-like concentrations, it would be detectable given enough observational time. If it is absent, that too is informative, ruling out Venus-like conditions and constraining the range of possible atmospheric compositions. Beyond carbon dioxide, the search for water vapor absorption features in the near-infrared would be the next priority. Water vapor detection would not by itself confirm liquid water on the surface, since water vapor can exist at high altitudes in cold trap limited quantities, even on planets without surface oceans. But its detection would confirm that the planet has not been completely desiccated by stellar radiation, and would open the door to further investigation of the water cycle in that atmosphere. The ultimate goal, the detection of disequilibrium biosignatures, lies beyond what Webb alone can achieve for TRAPPIST-1E. A simultaneous detection of oxygen, ozone, and methane would require not just higher sensitivity, but the ability to observe in wavelength ranges that Webb does not cover simultaneously with sufficient precision. That capability is what the Habitable Worlds Observatory is being designed to provide, and the planning that the DREAMS team is doing with Webb data is directly informing the scientific requirements being written for that future instrument. So the TRAPPIST-1 investigation is not a single campaign with a clear endpoint. It is an ongoing research program spanning at least 2 generations of space telescopes. Webb is the second chapter, following the Discovery chapter enabled by the TRAPPIST telescopes and the Spitzer Space Telescope. The Habitable Worlds Observatory, if funded and built on its current timeline, will be the third. The fourth chapter, if the earlier ones find compelling biosignature candidates, will involve missions specifically designed to characterize and confirm life, a goal that currently has no funded program behind it, but is the implicit destination of the entire trajectory. Standing at this particular moment in the story, the most intellectually honest assessment is that we do not know whether TRAPPIST-1E is habitable, whether it has an atmosphere, or whether any of the 7 TRAPPIST-1 planets have ever hosted or currently host life. The data is suggestive in places and ambiguous in others. The theoretical frameworks are sophisticated but not yet complete. The measurements are remarkable given the distance and the signal levels, but not yet conclusive. What we do know is that the question is legitimate, the target is the best available, the tool being applied is the most capable ever built for this purpose, and the research community pursuing this investigation is rigorous, creative, and genuinely motivated by curiosity rather than predetermined conclusions. That combination has historically produced real answers to questions that once seemed permanently out of reach. 40 light-years is a distance so vast it can be difficult to hold in mind. At the speed of light, the fastest anything in the universe can travel. Reaching TRAPPIST-1 from Earth would take 40 years. At the speed of the fastest spacecraft humanity has ever launched, the New Horizons probe, it would take roughly 800,000 years. In any practical physical sense, we cannot go there. We can only look. But looking, it turns out, can tell you an enormous amount. The fact that a telescope in space can detect the spectral fingerprint of a thin layer of gas surrounding a rocky world the size of our planet, orbiting a dim star 40 light-years away, by measuring the fractional change in a few photons of infrared light during a transit lasting a few hours, is not just technically impressive, it represents a genuine expansion of what the word observation means in science. For most of human history, observation meant looking at what was directly in front of you. The telescope extended that capacity enormously, allowing observation of objects millions of times fainter than anything the naked eye can perceive. The spectrograph extended it further, allowing observation not just of the brightness of distant objects, but of their chemical composition. Space-based infrared telescopes extended it further still, allowing observation of emission from molecules that are invisible to optical instruments. And now, transmission spectroscopy, deployed by the most capable infrared telescope ever launched, is allowing observation of the chemical identity of gases in the atmospheres of worlds that are, by any prior standard, impossibly far away to characterize. This is what science does. It extends the reach of observation beyond what current technology allows, step by step, building instruments that see more, measure more precisely, and extract more meaning from fainter signals. The question of whether the TRAPPIST-1 planet's host life is, at some level, simply the latest version of a question humans have been asking since the first person looked up at the night sky and wondered whether other worlds were like this one. The tools have changed almost beyond recognition. The question remains the same. There is a dimension of the TRAPPIST-1 system that rarely gets discussed in popular accounts, but that scientists working on it think about constantly. The question of time and the geological history these planets have already lived through. TRAPPIST-1 is estimated to be about 7.6 billion years old. Earth is 4.5 billion years old. That means the TRAPPIST-1 planets have been orbiting their star for more than 3 billion years longer than Earth has been orbiting ours. 3 billion years is a number so large that it requires some calibration. It is roughly the time from the first appearance of complex multicellular life on Earth, about 600 million years ago, back to the formation of Earth's oldest known rocks. It is longer than the entire history of animal life on our planet by a factor of 5. Whatever geological and chemical processes have been operating on these planets have had 3 billion additional years to work compared to Earth. This could be an advantage or a disadvantage for life, depending on which factors matter most. If an atmosphere was established early and has persisted, it has had billions more years for chemistry to develop, for potential proto-biological processes to run, for whatever chain of events leads from simple chemistry to replicating molecules. 3 billion years is almost certainly long enough for complex life to develop, given that Earth went from microbial life to multicellular organisms in roughly 3 billion years. But if the atmospheres were stripped early and have never recovered, then those extra 3 billion years are simply a longer record of barrenness. A planet that has been airless for 10 billion years is not more promising than one that has been airless for 7 billion years. The age of the system also matters because it affects the current activity level of the star. TRAPPIST-1 is older than our Sun and is in a more settled phase of its evolution. The worst flaring activity of a red dwarf's life is concentrated in its first 1 to 2 billion years, sometimes longer, but eventually the star settles into a routine that is still more active than our Sun, but far less destructive than its youth. TRAPPIST-1 has presumably passed through its most dangerous period and arrived at something closer to middle age by stellar standards, even though from a human perspective, that middle age stretches for trillions of years. If the TRAPPIST-1 planets had any atmospheres to lose, most of that loss probably happened during the star's first few billion years. What survives today is what made it through, and what made it through is what Webb is now trying to detect. There is also the question of biological time. Life on Earth did not appear instantaneously after conditions became favorable. The earliest evidence of microbial life dates to roughly 3.7 to 4 billion years ago, suggesting that life appeared within a few 100 million years of Earth's surface becoming hospitable following the late heavy bombardment period. But from microbial life to complex multicellular life took roughly another 3 billion years. The development of complex biology is not guaranteed by the presence of simple biology, and the reasons it happened on Earth when it did remain deeply uncertain. If life exists on TRAPPIST-1, it has had billions of years longer than Earth did to navigate that journey. If conditions were ever right, and if life got started, there is no particular reason to expect it to still be at the microbial stage. A 7 billion year old biosphere might have evolved complexity that we have no framework to anticipate. But this is speculation, and responsible science does not build too much on speculation. The immediate task is determining whether these planets have atmospheres, and if they do, whether those atmospheres have the chemistry that makes biology plausible. Speculation about the form life might take at TRAPPIST-1 is a conversation for after that more basic question is answered. The search for life around red dwarfs is, in one sense, a referendum on a century of assumptions about where life belongs. For most of the 20th century, the implicit model was that solar-type stars were the right environment, that life required a star roughly the size and temperature of our Sun in a planetary system configured roughly like ours. on a planet at roughly Earth's distance from that star. This model was partly observational convenience, because our own solar system was the only one anyone could study, and partly a form of cosmic parochialism, the tendency to assume that familiar conditions are necessary conditions rather than merely sufficient ones. The discovery of exoplanets in the 1990s changed the picture dramatically. Planets turned out to be essentially universal, found around stars of every type, in configurations often wildly different from our own solar system. Hot Jupiters, giant planets orbiting closer to their stars than Mercury orbits our Sunday super-Earths. Planets with masses between Earths and Neptunes that have no analogue in our solar system. Mini-Neptunes, puffy sub-Jovian planets in very different configurations. The universe's planetary portfolio is far more diverse than the solar system suggested. Red dwarf planets, because red dwarfs are so numerous, may represent the single most common type of potentially rocky exoplanet in the galaxy. If life cannot arise around red dwarfs, the universe contains fewer inhabited worlds by a very large factor. If it can, the implications for the cosmic prevalence of life are enormous. TRAPPIST-1, as the closest and most accessible red dwarf system with multiple rocky planets in or near the habitable zone, is the place where this question gets its first definitive empirical test. The scientific community has been careful about interpreting early Webb results in either direction. Negative results from B and C were not dismissed as evidence that the whole system is barren. Ambiguous results from D and E have not been prematurely inflated into evidence of habitability. This careful calibration reflects hard lessons from the history of the field, where premature announcements have sometimes damaged the credibility of legitimate research. The most famous example is the 1996 announcement by a team of NASA scientists that they had found evidence of fossilized microbial life in a Martian meteorite called ALH 84001. The announcement was made at a press conference that attracted worldwide media coverage. The claim was taken seriously enough to motivate President Clinton to deliver a public statement. But in the years following, the scientific community examined the evidence and concluded that none of the features cited as biological indicators, including the putative microfossils, the magnetic crystals, and the organic compounds, were unambiguous evidence of life. Each could be explained by non-biological processes. The claim is still debated, but has not been confirmed, and the experience reinforced how difficult it is to claim biological evidence in ambiguous datasets. The TRAPPIST-1 researchers are operating in that tradition of caution. The bar for claiming atmospheric detection is treated seriously because the bar for claiming biosignatures will be even higher. The scientific infrastructure being built now, the measurement techniques, the error analysis methods, the stellar contamination correction procedures, is the foundation on which any future extraordinary claim would have to rest. One of the most important conceptual developments in the field over the past decade is the recognition that a single biosignature gas is not enough. Oxygen was once considered the ultimate biosignature because, on Earth, the oxygen in the atmosphere is entirely produced by photosynthesis. Without biology, oxygen should rapidly react with reduced surface minerals and disappear. But astronomers have since identified abiotic processes that can produce oxygen in quantity, including the photodissociation of water vapor by ultraviolet radiation followed by hydrogen escape and the radiolysis of water by radioactive decay. A planet with a lot of water vapor and a lot of UV radiation could accumulate substantial atmospheric oxygen without any biology. Similarly, methane is produced by biology on Earth, but also by geology, through a process called serpentinization, in which water reacts with iron and magnesium silicates. The detection of methane alone around an exoplanet would not constitute evidence of life. What would be compelling is the detection of multiple gases in a combination that chemistry alone cannot maintain. Oxygen and methane together, as mentioned earlier, are chemically incompatible over long timescales without a replenishing source. If both are present simultaneously in detectable quantities, something is continuously making both, and biological metabolism is the most plausible candidate. This is the logic behind the design of the Habitable Worlds Observatory. Its instrument suite is intended to detect multiple atmospheric components simultaneously, including oxygen and its photolytic byproduct, ozone, water vapor, carbon dioxide, and potentially methane across a wavelength range that covers all of these signatures at once. The ability to observe the full atmospheric chemical fingerprint in a single measurement would allow the kind of multi-component analysis that biosignature science requires. But that instrument is still years away from launch. In the present, what TRAPPIST-1e represents is the best opportunity to develop the observational and analytical framework that will eventually be deployed for that purpose. Every transit observation, every improved stellar contamination model, every refined atmospheric retrieval algorithm built around the current Webb data is laying the foundation. In the history of astronomy, most of the really important advances have involved looking at something familiar in a new way, or with a new kind of instrument, and finding that it was not what it appeared to be. The sun's spectrum, analyzed in the 19th century, revealed the presence of elements unknown on Earth at the time. The Milky Way, photographed systematically, revealed a structure that the naked eye could not resolve. The cosmic microwave background, detected by instruments that were not looking for it, confirmed the hot, dense origin of the universe. The discovery that Type 1a supernovae at extreme distances were fainter than expected confirmed that the universe's expansion is accelerating. Each of these discoveries came from a combination of better instruments, more systematic observation, and a willingness to take seriously the implication of data that did not fit the existing picture. The investigation of TRAPPIST-1 is operating in that same tradition, and its most important result may not be the thing everyone is looking for. Astronomy tends to surprise. Whatever the ultimate answer turns out to be for the TRAPPIST-1 planets, the investigation will have produced a comprehensive map of the atmospheric diversity possible for rocky planets around red dwarfs, a refined toolkit for exoplanet atmospheric characterization, a more grounded theoretical framework for planetary habitability, and a much clearer sense of what to look for in the next generation of observations. That is a substantial scientific return regardless of whether any particular planet turns out to be inhabited. But the real prize, the one that drives the funding proposals and the telescope scheduling and the careers of the scientists involved, remains what it has always been. The possibility, still open, not yet ruled out, that somewhere in the TRAPPIST-1 system, there is a world where the chemistry has crossed the threshold that we have only ever observed in one place, and that a telescope 40 light-years away is about to detect it. That possibility is not certainty. Science deals in probability and evidence, not in hopes. But the probability is non-zero, the evidence so far has not eliminated it, and the tools now exist to test it. In science, that combination, a testable hypothesis with a real chance of being true, is exactly what makes a research program worth pursuing. The universe has been running its chemistry experiments for 13.8 billion years. The TRAPPIST-1 planets have been running theirs for over 7 billion. We have been watching them for less than a decade, with instruments capable of detecting atmospheric traces only for the past few years. The story is only beginning. Understanding why TRAPPIST-1e specifically has attracted the most scientific attention among the 7 planets requires looking more carefully at the numbers that define its position. The habitable zone of TRAPPIST-1 extends from roughly 4 million kilometers to roughly 9 million kilometers from the star, based on standard greenhouse climate models. TRAPPIST-1e sits at approximately 4.2 million kilometers, placing it almost exactly at the inner boundary of that zone. This is analogous to a planet in our solar system sitting at slightly inside the orbit of Venus, but receiving the equivalent energy level of Earth because the star is so much dimmer. The energy budget works out. TRAPPIST-1e receives about 66% of the stellar energy Earth receives from our Sun, keeping it in a range where liquid water is thermodynamically plausible. But its position within the habitable zone is just one factor. The planet's size, roughly 90% of Earth's diameter, places it in a range where planetary scientists expect geological activity to persist over long time scales. Planets much smaller than this, like Mars, lose their internal heat relatively quickly, reducing volcanic activity and eventually eliminating the interior convection that drives both geological renewal and the magnetic dynamo. Planets much larger than Earth develop more massive atmospheres and potentially retain more internal heat, but may also trap that heat in ways that are less favorable for surface habitability. TRAPPIST-1e is in the Goldilocks zone of planetary size as well as orbital distance. Its density, estimated from the combination of its transit measured radius and its gravitationally measured mass, is close to but slightly below Earth's, consistent with a rocky composition with some fraction of lower density material that could be water or carbon compounds. If it formed with significant water content and retained it, the planet could have a surface ocean. If the water was lost to space during the star's active early phase, the surface might be dry rock. The mass of TRAPPIST-1e is approximately 90% of Earth's mass. This is close enough to Earth's mass that many of the scaling relationships used to model Earth's interior and surface processes apply with only minor corrections. The planet should have a similar level of geological activity to Earth, similar potential for plate tectonics or at least crustal recycling, and similar timescales for volcanic outgassing of an atmosphere. The close mass match to Earth is part of why TRAPPIST-1e is the benchmark planet in the system for habitability discussions. But the fact that these numbers are favorable does not resolve the core uncertainty. We do not know if the planet has an atmosphere. We do not know if it has water. We do not know the current state of its interior. Webb is working to answer these questions, and each new observation adds signal, but the signals are at the edge of what current instruments can detect cleanly. One of the most sophisticated aspects of the Webb investigation is the effort to account for the star itself as a source of uncertainty. TRAPPIST-1 is not a simple, uniform light source. Its surface is covered in star spots and faculae, cooler and hotter regions respectively, that produce different spectral signatures from the surrounding stellar photosphere. When a planet transits and blocks part of the stellar disk, it may pass over or near these surface features, which changes the spectral signature of the blocked light. This is called the transit light source effect, and it is a significant source of confusion in exoplanet atmospheric spectroscopy, particularly around cool red dwarfs whose surface temperature variations between spots and photosphere produce large spectral changes. TRAPPIST-1's surface features, including its relatively numerous star spots compared to its photosphere, mean that the spectral signal during a planet transit can be contaminated by the variation in stellar surface composition rather than genuinely reflecting the planet's atmosphere. The DREAMS team has invested considerable effort in characterizing TRAPPIST-1's surface features at times when no planets are transiting, providing a baseline for the stellar spectrum that can then be used to correct transit measurements. This kind of stellar characterization work is not glamorous but is essential. The difference between a claimed atmospheric detection and a stellar surface artifact can be the difference between a Nobel Prize and a retraction. The methods being developed for this correction are pushing the limits of stellar astrophysics as well as planetary science. Understanding the photosphere of a cool M-dwarf star well enough to subtract its contribution from a transit spectrum requires modeling the physics of stellar granulation, convection, magnetic field emergence, and spot formation in regimes where theory is still being developed. TRAPPIST-1 is, in this sense, advancing stellar astrophysics as well as planetary science. There is also the matter of what happens to the planet's atmospheres during flares rather than in steady-state conditions. Stellar flares produce brief but intense bursts of radiation across the electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. The impact of a single flare on an atmosphere is temporary. The accumulated impact over billions of years of flaring is not. During a major flare, the sudden increase in ultraviolet radiation causes photochemical reactions in the upper atmosphere that can destroy molecules, in particular ozone. Ozone is the primary shield against ultraviolet radiation in Earth's upper atmosphere. On a planet without ozone protection, ultraviolet radiation from a flare would penetrate to the surface, potentially sterilizing surface life or damaging complex molecules. On Earth, the ozone layer is maintained by the continuous photodissociation of oxygen molecules by solar ultraviolet radiation and their recombination into ozone. A planet orbiting TRAPPIST-1 with an oxygen-containing atmosphere might have a more dynamic ozone cycle than Earth, with the layer depleted during flares and rebuilt during quiescent periods. This is not necessarily fatal to life. Life on early Earth existed when the ozone layer was far thinner than it is today because atmospheric oxygen had not yet built up to present-day concentrations. Early life on Earth survived with far more ultraviolet exposure than modern surface life experiences. Some organisms, extremophiles that thrive in high UV environments, are thought to be descended from these early lineages and retain UV resistance mechanisms that other modern organisms have lost. Life around TRAPPIST-1 might show similar adaptations, if it exists. The possibility that flares could actually drive the origin of life by providing the energy to synthesize RNA precursors from simpler chemicals, while also demanding that any life that arises develops resistance to UV damage, is an interesting evolutionary pressure. It selects specifically for organisms capable of repairing molecular damage quickly, perhaps resulting in biology with different genetic architectures than Earth's, but not necessarily less complex or less capable. This line of reasoning illustrates why the search for life at TRAPPIST-1 is not simply a search for Earth's twin. it is a search for the range of conditions under which life of any kind can originate and persist. Earth's particular history is one path through that space. TRAPPIST-1, if it harbors life, took a completely different path, under different radiation conditions, around a different type of star, in a completely different dynamical environment. The biology that resulted, if it resulted in biology at all, might be startlingly different from anything on Earth, or it might be remarkably similar because the underlying chemistry of carbon-based molecular systems may converge on similar solutions regardless of starting conditions. That question, convergence or divergence in the evolution of life under different conditions, is one of the deepest in astrobiology. Earth provides exactly one data point. TRAPPIST-1, if it turns out to be inhabited, would provide a second. With 2 data points, the field could begin to distinguish between what is specific to Earth and what is general to life. With dozens of inhabited worlds across different stellar environments, the general principles would become clear. This is why the detection of life anywhere beyond Earth, even microbial life in a subsurface ocean, even chemical biosignatures in a planetary atmosphere detected remotely, would transform biology as profoundly as any discovery in the history of science. Biology currently has a sample size of 1. A sample size of 2, even if the second data point is distant and difficult to characterize, immediately allows comparative analysis. And comparative analysis is how science distinguishes coincidence from law. The TRAPPIST-1 investigation, whether or not it finds life, is building the methodology for that comparative project. The atmospheric characterization techniques being developed now, the stellar contamination models, the atmospheric retrieval algorithms, the biosignature frameworks, will be applied to dozens of systems in the coming decades. Some of those systems will present stronger or weaker biosignature candidates than TRAPPIST-1. The decisions made about how to interpret ambiguous data in the current investigation will set precedents for how similar decisions are made in future investigations. Getting those methodological precedents right is arguably as important as any specific scientific result from the current campaign. Science is a cumulative enterprise, and the norms and methods established at the frontier of a field shape its trajectory for decades. The TRAPPIST-1 system will continue to be observed. Webb will keep collecting transits. Future ground-based spectrographs with larger collecting areas will add complementary data. The next generation of space telescopes will bring higher sensitivity. And eventually, the Habitable Worlds Observatory will bring the specific capabilities needed to search for biosignature gas combinations. The question that began this investigation, are any of the TRAPPIST-1 planets conducive to life, is not going away. And the answer, when it finally arrives in whatever form science delivers it, will matter for how humanity understands its place in a universe that may be, or may not be, full of other minds looking back. If you have found this kind of question worth thinking about, worth following as the science develops, then the story of TRAPPIST-1 is one you will want to stay close to. Like and subscribe to keep up with new developments as they emerge, because the TRAPPIST-1 story is far from finished. Each Webb observing season brings new data. Each new analysis refines the picture. The decades ahead will see this system's secrets, whatever they are, come into focus. It is worth stepping back for a moment and considering the broader context in which the TRAPPIST-1 investigation is taking place. We are living through what may be one of the most scientifically consequential decades in human history, specifically with respect to the question of life beyond Earth. Multiple converging lines of research are advancing simultaneously, and TRAPPIST-1 sits at the intersection of several of them. The first line is planetary detection. Since the 1990s, astronomers have confirmed the existence of more than 5,500 exoplanets, with thousands more candidates awaiting confirmation. The statistical picture that has emerged from this census is extraordinary. Rocky planets in the size range between half and twice Earth's radius are extraordinarily common around stars of all types. Around red dwarfs specifically, which are the most numerous class of stars, rocky planets in the habitable zone appear to be more common than rocky planets in the habitable zone of Sun-like stars, simply because the habitable zone is so close to the star that the geometric probability of a planet forming there is higher. Estimates suggest that approximately 40% of red dwarf stars host rocky planets within their habitable zones. There are approximately 100 billion red dwarfs in the Milky Way. 40% of 100 billion is 40 billion potentially habitable rocky planets in our galaxy alone, around red dwarfs only, not counting planets around larger stars. The number is staggering. and it has shifted the probability calculus of life in the cosmos dramatically toward the optimistic end. The second converging line is the biochemistry of extreme environments on Earth. In recent decades, biologists have catalogued life in settings once thought completely uninhabitable. Microorganisms thrive in the boiling water of deep-sea hydrothermal vents, in highly acidic volcanic springs, in extremely alkaline lakes, under kilometers of rock in deep mines and boreholes, in the frozen brine channels within Antarctic sea ice, in the dry valleys of Antarctica where conditions closely resemble Mars, and even in the stratosphere where cosmic radiation levels are extreme. Each new extreme environment found to contain living organisms extends the range of conditions under which biology is possible. The concept of extremophiles, organisms adapted to extreme conditions, is now central to astrobiology. The discovery that life is not confined to the mild temperate zone of Earth's surface, but extends to virtually every environment where liquid water exists, even intermittently, has dramatically expanded the parameter space considered biologically accessible. This matters directly for TRAPPIST-1, where conditions might be more extreme in some dimensions, but potentially within the range that extremophile biology could tolerate. The third converging line is the chemistry of interstellar space and planetary formation. Astronomers using radio telescopes have detected more than 200 distinct molecules in the interstellar medium, including amino acids, sugars, and complex organic compounds. These molecules form through chemistry, driven by ultraviolet radiation and cosmic ray bombardment of ice-coated dust grains in molecular clouds. They are then incorporated into the material from which planets form. Every rocky planet in the universe is, to some degree, seeded with organic chemistry from the interstellar medium before its history as a planet even begins. This means the raw materials for life are not unusual. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the 6 elements most central to biochemistry on Earth, are among the most abundant in the universe. The specific molecules that form the backbone of Earth's biochemistry, amino acids, nucleotides, lipids, sugars, have been detected in meteorites and comets. These molecules are being delivered to planetary surfaces throughout the history of planetary systems, providing a constant supply of pre-biological chemical complexity. For the TRAPPIST-1 planets, which have been orbiting their star for more than 7 billion years, there has been substantial time for cometary and meteoritic delivery of organic material. The system's compact orbital architecture means that cometary bombardment patterns might be different from what occurred in our solar system, but the basic supply of organic chemistry from space is a feature of every planetary system, not a peculiarity of Earth's. The fourth converging line is the increasing capability of Earth-based and space-based observatories. Webb is not the only instrument advancing exoplanet characterization. The Atacama Large Millimeter Array, or ALMA, has detected complex organic molecules in protoplanetary disks around young stars, showing that the building blocks of life accumulate in planetary systems as they form. The Espresso spectrograph at the Very Large Telescope in Chile is measuring stellar radial velocities with such precision that it can detect Earth-mass planets in habitable zones around nearby stars. The European Space Agency's CHEOPS mission is precisely measuring the sizes of known exoplanets to constrain their densities. And the upcoming Plato mission from ESA, scheduled for launch in 2026, will survey hundreds of thousands of stars for transiting planets, with a focus on Earth-like planets around Sun-like stars. Each of these programs contributes a different piece of the picture. Together they are building a comprehensive empirical understanding of the distribution, composition, and atmospheres of rocky planets across a wide range of stellar environments. TRAPPIST-1 sits near the top of every priority list because it combines the most favorable observational geometry, the most accessible atmospheric signals, the most Earth-like planet sizes, and a star type that is statistically dominant in the galaxy. The resources being devoted to this single star system reflect how seriously the scientific community takes the possibility that the answer to one of humanity's oldest questions might be hiding there. Guaranteed web time, one of the most competitive and coveted resources in current observational astronomy, was allocated to the TRAPPIST-1 campaign specifically because the case for it as a biosignature target is stronger than any other currently accessible system. There is also a dimension of this investigation that relates to the longer-term trajectory of human exploration of the universe. Even if no life is found in the TRAPPIST-1 system, The technologies being developed to characterize these worlds from 40 light-years away are prototype technologies for an era of cosmic exploration that currently seems science fictional, but that the scientific trajectory suggests is not. Impossibly remote. The ability to remotely sense the atmospheric chemistry of an exoplanet from an orbital observatory is conceptually the same capability that would allow a probe in the outer reaches of a target star system to characterize planets there, without entering their atmospheres. The biosignature frameworks being built now are the same frameworks that would guide any autonomous probe carrying instruments to a target system. The deep understanding of stellar contamination effects being developed for TRAPPIST-1 would apply equally to any mission that needed to observe a planetary atmosphere near a red dwarf star. None of this makes interstellar exploration imminent. The engineering and energy requirements for even the smallest probe capable of reaching another star system within a human lifetime are orders of magnitude beyond anything currently developed. The smallest plausible interstellar probe concepts, like the laser sail concept developed by the Breakthrough Starshot initiative, would weigh a few grams and be accelerated to a significant fraction of the speed of light by a gigawatt-scale laser array. At 20% of the speed of light, such a probe would reach TRAPPIST-1 in about 200 years and require another 40 years for the signal to return. A voyage of 240 years to receive a single flyby observation is not a near-term scientific program. But the point is not that interstellar travel is around the corner. The point is that the science being done at TRAPPIST-1 today is building the knowledge base that makes any future interstellar investigation more meaningful. Knowing which of the TRAPPIST-1 planets to visit, knowing what their atmospheres contain, knowing what signatures of life to search for, knowing the stellar environment that any instruments would be operating in, all of this requires exactly the kind of comprehensive characterization that Webb and its successors are undertaking now. In that sense, every transit observation of TRAPPIST-1e is not just science for its own sake, but investment in a project that extends far beyond any currently living scientist's career or lifetime. The questions being asked now about TRAPPIST-1 are the same questions that future scientists, possibly using technologies not yet imagined, will still be asking about other systems around the universe. The methods being developed now are the intellectual infrastructure for that future project. The scale of this perspective, from individual transit observations lasting a few hours to multi-generational scientific programs spanning centuries, can be difficult to hold in mind. Science routinely operates on timescales that exceed individual human lives, from the century-long program of stellar classification that produced the Hertzsprung-Russell diagram to the decades-long development of general relativity's predictions before tests became possible, to the multi-generational effort to understand the formation of planetary systems. The investigation of TRAPPIST-1 sits in that tradition. What makes this moment unusual is the acceleration. The first exoplanet was confirmed in 1992, just over 30 years ago. In those 30 years, the field has gone from a single ambiguous detection to a catalogue of thousands of confirmed planets, a precise determination of the frequency of Earth-like planets in habitable zones, the first detection of molecular features in exoplanet atmospheres, and now, with Webb, the first serious attempt to characterize the atmospheric chemistry of potentially habitable rocky worlds. 30 years is a geological eye blink. It is also roughly a scientific generation. The scientists who began their careers when exoplanets were theoretical possibilities are now senior researchers overseeing programs that would have seemed impossible when they started. The scientists entering the field today will see capabilities that make Webb look like a first-generation instrument. The TRAPPIST-1 system will be observed throughout that transition. It will be one of the most thoroughly characterized planetary systems in the galaxy by the time the Habitable Worlds Observatory delivers its first results. And if any of its planets turn out to harbor life, the documentation of that discovery will span everything from the earliest TRAPPIST telescope transit curves to Webb spectral retrievals to the biosignature measurements of a third-generation space telescope, a 30-year arc from possibility to confirmation. If instead the system turns out to be biologically empty, that result will be equally important, establishing that even a well-positioned red dwarf system with multiple rocky planets in the habitable zone is insufficient for life. That result would motivate the search for what additional conditions are required, and would shift the probability distribution for life's occurrence in the galaxy in ways that no amount of theorizing can substitute for. Either answer advances the science. Either answer is worth finding. The current state of knowledge, then, is best described not as a failure to find life, but but as the construction of the evidential foundation upon which a future finding in either direction will rest. Science builds slowly. The most important questions take the longest to answer. And the TRAPPIST-1 investigation, still in its early observational phase despite the sophistication of the instruments involved, is building that foundation with care and rigor. 40 light-years is not so far. Light crosses it in a human lifetime. The signals are faint but real. The instruments are ready. The questions are clear. And the patience required to let the science do what science actually does, accumulate evidence until the picture becomes unmistakable, is the same patience that has always been the defining characteristic of the best science. The universe has kept this particular secret for 7 billion years. We have been seriously looking for about 10. There is no reason to rush and every reason to keep watching. Return, for a moment, to the detail that started this whole investigation: 7 rocky planets, all of them roughly Earth-sized, most of them within the habitable zone, all of them orbiting a single dim star 40 light-years away. That fact has not changed. What has changed, through years of progressively more sensitive observations, is our understanding of what those 7 planets are actually like. The picture that has emerged is more textured, more complicated, and more scientifically rich than the simple catalogue of orbital parameters suggested when the system was first announced in 2017. The 2 innermost planets, TRAPPIST-1 b and c, are almost certainly barren. Webb has closed off the atmospheric possibilities for them to an extent that makes habitability implausible under any reasonable model. This is not a failure, it is data. Knowing what B and C are tells you something about what the star's radiation environment has done to the closest planets and provides context for interpreting what has or has not survived further out. Planet D is ambiguous and probably less massive than the threshold needed to retain a dense atmosphere easily, though it has not been definitively ruled out. Planets F and G sit in the outer region of the habitable zone, where water, if present, might be locked in ice or steam rather than liquid. Planet H, the outermost, is probably too cold unless unusual atmospheric chemistry provides unexpected warming. And TRAPPIST-1e remains the focal point, not because its situation is unambiguously favorable, but because it is the most carefully balanced. The right size, the right mass, the right orbital distance, an atmospheric signal that has not been clearly detected but also has not been clearly ruled out, a star that is hostile but not uniquely so, a system that is old enough to have run its chemistry for a long time but that has also been bombarded for a long time. Every parameter that matters sits in a range where both positive and negative outcomes remain physically possible. That is precisely why it is the most scientifically interesting planet in the nearest multi-planet habitable zone system we know of. The measurements Webb is accumulating, one transit at a time, are the best tool currently available for determining which side of that balance TRAPPIST-1e falls on. And the careful, rigorous, patient science being done by the researchers analyzing that data is the best approach currently available for turning raw measurements into reliable knowledge. That knowledge will come, maybe not this year, maybe not in this decade, but it will come. The instruments exist, the targets are known, the methods are being refined, and the question is real. Whether the TRAPPIST-1 planets are alive, dead, or somewhere in between, the investigation of them is one of the great scientific endeavors of this era. And the answer, when it arrives, will be among the most consequential facts our species has ever learned. The comparison between how we looked at the TRAPPIST-1 system in 2017 and how we look at it today illustrates something important about the nature of scientific progress. In 2017, the excitement was driven by discovery. 7 rocky planets, habitable zone positions, Earth-like sizes. The announcement triggered an enormous wave of public interest precisely because it described a system that seemed, on paper, almost designed to be hospitable. But science never stays at the discovery stage. The measurement work that follows, the patient, unglamorous, technically demanding work of actually characterizing what was found, always complicates the initial picture. The TRAPPIST-1 planets, when studied closely, are not simply small Earths in convenient orbits around a convenient star. They are complex worlds, shaped by billions of years of radiation, tidal forces, geological evolution, and orbital dynamics in a system quite different from our own. The star is cooler and more active than our Sunday. The orbital distances are compressed into a space that would fit inside Mercury's orbit. The tidal locking creates permanent day and night hemispheres on every planet. The stellar flares hit harder and more often than anything in our solar system's current environment. The timescales of stellar aging are stretched to trillions of years rather than billions. None of these differences are automatically fatal to life, but none of them are automatically harmless either. What the Webb observations are doing is providing the empirical evidence needed to determine, planet by planet, which of these factors dominate and what their consequences are for surface conditions and atmospheric chemistry. The inner planets have provided clear answers. The middle planets are providing ambiguous but genuinely informative data. The outer planets await more detailed investigation. And TRAPPIST-1, the most carefully studied of the set, is providing data complex enough that the community is being careful not to read more into it than the measurements support. This caution is not timidity. It is the correct epistemic response to data at the edge of detectability. The history of science is littered with premature announcements based on measurements that turned out to be noise, artifacts, or misinterpreted signals. The TRAPPIST-1 team is determined not to add to that history. The bar for any claim about this system is set appropriately high. What that means in practice is that the story of TRAPPIST-1 will unfold slowly, not because the researchers are moving slowly. They are working as fast as the telescope scheduling and the data analysis pipelines allow, but because the universe delivers its information on the universe's schedule and the signals involved are at the limit of what current technology can resolve. More observing seasons will pass, more transits will be recorded, more analysis will be done, the picture will sharpen, and at some point, the data will be clear enough to say something definitive. Either there is an atmosphere on TRAPPIST-1 or there is not. Either there are molecules in that atmosphere consistent with biology, or there are not. Either this system is alive in some way, or it is the kind of extraordinary arrangement of potentially habitable worlds that life simply never got around to inhabiting. Both answers are scientifically valuable. One is cosmically transformative. The possibility that we might be living in the decade or the generation that finds the first clear evidence of life beyond Earth is not something that requires speculation to take seriously. It requires only a clear-eyed look at the current state of the science, the capabilities of existing and planned instruments, and the quality of the target being studied. The pieces are in place. The question is real. The answer is within reach. We are watching. There is one more thing worth considering as this investigation continues to unfold. The question of life beyond Earth is not purely scientific. It sits at the intersection of science, philosophy, theology, and human self-conception in a way that very few empirical questions do. The discovery that we are not alone in the universe would not simply be a data point. It would be a redefinition of what it means to be human, of what the universe is for, of what the long arc of evolution and civilization on this planet adds up to. Most people, if asked directly, say they believe some form of life exists somewhere in the universe beyond Earth. The universe is vast, they reason, and it would be strange if this one small world were the only place where chemistry found its way to self-replication. That intuition is reasonable, perhaps even statistically well-grounded, given what we now know about the frequency of rocky planets and the ubiquity of organic chemistry. But intuition is not evidence, and the difference between believing life is out there and knowing it is there is the difference between a philosophical position and a scientific fact. The TRAPPIST-1 investigation is part of the machinery by which that belief might be converted into knowledge, or, alternatively, part of the machinery by which a particular candidate for that knowledge is tested and found lacking. Either way, the machinery is working, the process is underway, the investigation is real. To follow it is not merely to follow a news story about a distant star system. It is to be present at one of the defining scientific investigations of the century, one that may or may not produce the most consequential discovery in human history, but that is building the foundation for that discovery, whether or not TRAPPIST-1 turns out to be the place where it happens. The universe is 46 billion light-years across in its observable extent. It contains 2 trillion galaxies, each with hundreds of billions of stars. The region of it accessible to detailed study from Earth is, in cosmic terms, minuscule. But it includes, within 40 light-years of us, a system of 7 rocky planets orbiting a long-lived red dwarf, at least one of which sits in the habitable zone with a size, mass, and orbital position that allow the question of life to be asked with more than theoretical seriousness. That is not nothing. That is, in fact, an extraordinary configuration for a universe that did not have to arrange itself with any particular regard for what any organism on any particular planet found interesting or scientifically accessible. Whether TRAPPIST-1e is alive is a question we cannot yet answer. Whether the investigation of it is worth pursuing is a question that answers itself.